feel to it.
Yeah, it's got an almost improvisational tone.
This semester on Stat 201, prepare yourself for YouTube, because we're all zoomed out. Cahoots and special guests, Tiny Brian, Puppet Shark, Evil Moobot,
I am Yeja.
Morty the Rabbit, and more. Super Statistics Bros.
Oh my gosh, what questions do people have? I'm so bright again. It's so bright. Look at this. My head disappeared. Oh my, look, just disappear. It's crazy. How's everyone doing? Woodson, good to see you there. Good to see John in the chat. Who has questions? I feel like, let me change the brightness. Ask questions. Ask questions. Carson! Can you hear me, Carson? Can you hear me, Carson? I'm changing the brightness. There we go. It's too bright. There we go. Yeah, a little better, a little better. What's up, Carson? A little better. I'll get those bright lights. Get the monster energy. Howdy, good to see you there, Ethan. You can check points. Mubot is awake. Who has questions about anything going on with the test or anything? We made a Juva Verity video. It's got some views. My wife was like, did you make an AI thumbnail? And I was like, I did, because I didn't want to make one on my own. So I made an AI thumbnail. 110 views. That's a lot of views, actually. It's a lot more views than we usually get. So maybe more people will be watching. And I might do it on the scientific one, too. Would people want that? Would you want one on the scientific calculator? Hey, Brian, it's a grade calc. It is accurate. It uses what we have. So good question, John, right there. It uses what we have. So if you go through and enter things in, it uses our grade percentages. So it should be accurate because it's what the grades are. You just go in and do the what if scenario. Good question right there. I like that. The what if scenario. Let's do some practice problems. You're welcome, John. Anytime. Glad to answer questions. Let's see. I just got an email from myself. I'm going to go unread. That's going to be a watch later for the a lot of people were having issues with the calculator, so I was like, let me make a video going over it. Traffic alert. Oh, that's out later. So many emails. Good to see you, Mackenzie and Admire. Good to see you there. Okay, let's do this. Traffic alert. WWE tonight. What? WWE is going to be here? Oh, man. Just walk around campus. See some WWE. Surely they would check out our campus, right? Surely. Well, it's looking crazy outside. Okay, with that said, I'm just going to we'll do the hair thing. Go do the hair thing. I tried to talk to their support chat thing, and they were, in fact, not helpful. I'm sorry, Mackenzie, about that. I might be able to, you know what I could maybe do? I have an idea. Let's try something, then we'll get serious. Megan, good to see you there. Can you confirm the timing on exam? That is true, but if you click, it says it opens at 6:15. That is accurate. It says it's open from 6:15. Oh, it says 6. Oh, Megan, you're helping me out right here. I wish I could give points. Let me wait.
Megan, thank you from Ubot. I have no more points, but Brian is fixing it right now.
Okay. Mubot thanks you. Let me go fix this because that is wrong. It's been a crazy with Canvas going down. There was an error with the thing, and then apparently I put 6:15 a.m. So it's supposed to be 6:15 p.m. and we need to do what the other classes do. If you do have extended time, I did open it early so that way you could use your extended time because some people have like time and a half with accommodations. So I made sure it was open early enough. So 6:15 right here. I would throw you points, but it should be fixed now. Should be fixed. We don't want like every other section to be like, why is there a section get it all day? I have a question about the exam for the formula sheet. Can we write it on it once the exam starts? True. Yes, Maddie. Exactly. Totally, you can do that after the exam starts. You might even, and it really helps us out if you just want, I've knocked everything off my desk currently. So if you just want to like hold up your formula sheet and be like, hey, nothing's written on it now, just that can help. What's the time limit? I believe it's 90 minutes. Let me go look. What's this? Edit. Let me go look. And the time limit is, I think, 90 minutes. There's a 90-minute time limit. Any other questions? We'll put right here, ask questions about the exam. I'm going to try to do something too. Questions about the exam. Questions about the exam. The better, like what we just think about, like with what you can see with the camera, you don't want to be in frame where you're just seeing your head like this. You want to keep your head towards the top of the frame, because we don't need to see your hair. I mean, we can, but like the more you're in frame, the better. Like if you're hunched over, we talked about that. Mackenzie, great questions right here, because you don't want to be like this in frame. That's so horrible. It's just gonna make the worst faces. When you be like this, you look all crazy, like. But don't be all like, sit up in frame, sit at a chair, sit at a desk. And that way we can see what, like, to a certain extent. Does that make sense? You don't, because we just have some issues. I think you can understand as professors and instructors that you get this like that, but it's more like people are framed up. Yeah, that's great. Yeah, it's good, Grace. Don't worry if you're not cheating. I would say it's gonna be like we're making a bigger deal out of it than it is. Like a lot. I understand the worry. I don't want people overly worried. Like if you nervously look to the side every once in a while, that's not a big deal. If you slouch for a moment, that's not a big deal. If you take your whole exam and we can only see like from here up on you, and you're constantly like looking down and looking around and like constantly, and there's other, I don't want to tell you everything that we check for, because then people are like, oh, they check for that, check for that. I promise you, we've had a very high success rate of people admitting when we call it out. And I want to say thank you to people who have admitted it, because that makes our life way easier. Does that all make sense? Like, we have had to talk to people about it, and a lot of people straight up admitted it. Straight up. And there's a lot of things that you can see that, like, you're like, I don't want to say everything, because then people are like, oh, this is how I should not show that. You probably answered this, but I have 1.35 mute. Yes, that is true right there, Emerson. Great work. That's what you get. So make sure to take a screenshot just of that right there, just of what it shows, and that's what you get. Oh, no, Mackenzie, don't worry. Yeah, I think I promise you, most people are like, unless you're constantly looking that, like, I don't want anyone to have anxiety over this. I always look for concrete evidence. I'll tell you this much. Everyone I've spoken, I'm so happy, because this semester, everyone I've spoken to, and I've spoken to maybe not 6, 7 people, a few less. But Mackenzie, if this makes you feel happy, everyone I've spoken to this semester about cheating has admitted it. And they admitted it pretty quickly. Does that make you feel a little bit better, Mackenzie? I know ADD. I am patient, zero ADD. But everyone I've spoken to admitted to it. Just straight up admitted. I have a 100% rate, which I like to keep. I like to keep my 100% rate, that when I go to someone and I'm like, hey, something's going on right here, and here's what I'm seeing, and they're like, yeah, you caught me. Does that make sense? And does that make you feel a little bit better? Brian has 100% of people admitting when he goes to them. I'm proud. I am proud of that, because every time a student says, which it has happened in the past, but then they're found guilty of student conduct, and it's been more in the past, it's been more on projects and stuff, where they're like, I didn't know I couldn't get work sent to me, which my syllabus clearly outlines and everything. I just show you, just be like, there's my ear. We're just making sure you don't have like earbuds in. Sometimes we have people take tests with like headphones on. You can't take with headphones on. We know what you're listening to. Does that make sense, Joshua? Just give it a quick like, hey, nothing in my ears. Like, you don't have to be like, does that make sense? Just a quick like that. I would feel guilty to even consider cheating. I just get scared. I will be fine. Yeah, I promise you, it's really a big deal to me to accuse someone of cheating. A big deal. It should be, right? And with that, I like keeping my 100% rate. Now, some students will not admit to it. And I've had students where, here's a story from years ago. Of course, no names attached. But we had a whole cheating ring that we knew there was projects being passed around because we use a program. Sure, if anyone knows, it's called WCopyFind. It's the name of the program we use. And this guy who's a computer programmer made it, and it's better than Turnitin. So we use Turnitin, and then we use this program, which is not like an online program. You actually run it local to your computer. You can find it. It's called WCopyFind. So this is the cheating ring right here. That's some commitment. Well, what it was it was the project, and they had all sent around the project to each other, or it might have been in some like bank of like former projects. So we knew that it was connected to this project. Like, this one project was the originator, and then everyone had like large chunks from that project that were word for word identical. And everyone was saying like, I have no idea what you're talking about. I have no idea. And this is like a decade ago, I'll say. Yeah, this one person was like, we're going to sue you. I was like, you're going to sue me? And they're like, for these false accusations. I was like, and I was a newer teacher, so I was a little scared. I was like, you're going to sue me? And then someone turned in the work with the name of the student we knew it was all connected to on it. Like, someone actually turned it in, was like, here's my project. And they didn't change the name at the top. We're like, you are the laziest cheater ever. And so it was like, yeah, this is all connected, and everyone got in trouble. But they said they're going to sue me. It's like, what? What? Because they're trying to, it's basically gaslighting, right? They're being like, you're not seeing what you're seeing. And it's really sad that some people, yeah, the world's worst cheaters right there. And it's really sad and really tough that some people will go to further lengths and accuse the professors of wrong. So this semester, everyone's admitted to it flat out. Thank you. If I've spoken to you about cheating and you admitted straight up to me that you cheated, thank you. I mean that. I hate having to draw the truth out of people. Because I usually ask once in a vague way, and I say, hey, I'm seeing some stuff here. Anything you want to tell me? And everyone pretty much told me, like, flat out. They were like, here's what happened. Here's what I did. I'm sorry. And that's very good to hear. It's what you want. It's the best. Let me just put it this way. If you're watching this and you've cheated, you get called about cheating, I promise you instructors go lighter when you admit that you've cheated. It's not like a trick. Don't cheat and then admit to it. That's bad. But the penalties we can give up to the syllabus penalty. Like, the syllabus outlines the penalty, and in Stat 201, the biggest penalty is an F in the course. So the best thing to do is, if you cheat, just admit to it. Honesty is the best thing. Exactly. It's better to be honest midway through the process and do the honest thing than push it through. With how much work the analytics assignments took, I don't even know how you would cheat without it just fully copying. Well, we've seen people fully copy. We've seen people fully copy. We've seen people use people's other work as like a skeleton, as like a template, which you're not allowed to do. Syllabus clearly says. So you see a lot of that. And then there's certain thresholds we have. Like, put it this way, and then we'll talk about something else here. I try not to make any type 1 errors. So once I get below a certain level of evidence, I throw it away. Like, we try to do like blatantly. I spent like 7. Thank you so much, Mackenzie, right there. Yeah, I really appreciate you working really hard on that, working hard on the project. It's really awesome. And I hope you learned about some stats. Now you know how to make some graphics. You know how to do some analysis. You know how to talk about p-values, the slope, the intercept, the r-squared, the p-values. P-values are very important. They're the probability of our results or results from our stream happened by random chance variation given that the null is true. Any other questions about the exam or about cheating or what's going on? I was going to try something. I'm going to try in the background right here. Let me go grab that Yeja Verity. Oh, I can go to my, let me go to ChatGPT. I'm going to try something. There's no, everything will be graded pretty instantaneously. There should be no short answers unless my exam didn't sync. Yeah, people have already taken it and it's not asking me to grade. Will an applet screen on the test so we can memorize the T's and Z's? We'll give you all the T's and the Z's. Good question. T's and Z's for 68 are basically 1, for 95 basically 2, and 99.7 basically 3. The 90 is 1.645, 95 is 1.96, 99 is 2.5758, but you don't need to memorize them. Good question, Williams right there. Olivia Williams. Go ask more questions that you have. I'm going to try to do something right here in the background. I'm wondering if this will work. I had this crazy idea, and I want to see if it works. Please ask any and all questions about the exam. Then we'll probably do some practice questions. But this is your point right now, just to hop on, ask a question about the exam, even if someone's already asked it. And so, business analytics. Oh, why did I not see that? I'm gonna do something cool. I'm gonna remake the. I wish I could work with the Yeja Verity people. One, their tech support needs to be better. And 2, why can't they just do a simulated TI calculator? Like, I know they're like the regular or the scientific. Why can't they just simulate it? I might do collateral. Oh, that's awesome, Josh. Yeah, accounting and business analytics. Basically, business analytics is just like data interpretation skills, data visualization skills, data communication skills. And I always think like pairing it with like a collateral or something. We see a lot of supply chain business analytics, but think about like it's just the analytics of business. It's just numbers and figures and communication. When I finish the exam, it'll be great instantaneously. It will, but we're not showing the grades, I think, or the results yet. We kind of wait on that. Business analytics right there. I'm tempted to switch. Oh wait, is it in major to marketing and do some sort of marketing? Yeah, you could. My sister does marketing. She does Newtonox. I love shouting out my sister right here. She got a marketing major from Glocker before we were Haslam. So my sister is a marketing major. I do not have a business degree. Don't tell anybody. I have a psychology degree. Don't tell anybody. Can you break down what to expect to see on the test specifically? Jenna, yeah, we'll do that next right here. I'm going to try this, and then Jenna, we will do your question next. What to specifically expect to see. I'm going to try a crazy idea. I keep saying I'm going to do it, and let's try this. Let's go to Neutron. Okay. I need you to make a shiny app of the Yeja Verity calculator. Here is what it looks like. Make this into a shiny app so that anyone can use it. Wait. Sure, let's try it. I'm torn between that and business analytics. Maybe I'll do it. Yeah. I would say the biggest thing, and here's the best thing. Your major matters, but it's more what you do. And Mackenzie, I'm going to read that here in a second about Pittman, because Pittman's awesome. It's more what you do when you're in college, like the connections you make, the internships you try out for and you get, the people you meet, because there's like, you can graduate with any degree and it'll be worthless if you haven't actually like made connections, talked to people, know people in industry. And so we have the Business Analytics Forum. Actually, was just getting emails about that this morning. And we put students in front of employers early on. So we're trying to get the employers here, which we do. Bush's Baked Beans, Clayton Homes, Amazon. Trying to think who else we got. Oh, Nissan, Tractor Supply. I want to do a big project with them with the honors class next semester. So we've got tons of people. You can look at our wallet there and keep naming. I think I've named current ones, might name past ones. But like we're always working with and trying to get students in front of employers. Exactly. And Ian said it right there perfectly. You can make it a minor. I think the biggest thing is focus on your connections, who you meet and what you learn. Because that's really going to, I think, help out like your connections and everything. Oh my gosh. Look what we have here. You're about to see it. Is it going to work? Let's go to the main screen. Let's check it out. I really want to make this so we have an offline Yeja Verity calculator. It might actually work. 3 plus. Oh, it's even better. It actually shows you on the screen. So in seconds here, I just want to point out, in seconds, it's a little off the screen though, but in seconds right here, we have made a Yeja Verity calculator where you can actually see 3 plus 6 plus 9 equals. You want to contact Yeja Verity and be like, hey, this guy will, and it'll make it so you can see the full thing. And then we hit AC to clear right there. And you go like 33 square root and it shows you, and it's a little bit off the screen. We just need to resize it. Yeah, exactly. It's almost like maybe that thing should say clear. I know it says AC, but why not? You can just like make it say clear. Oh, it doesn't have the scientific yet. Yeah, I mean, look at this. You can actually see what's on the calculator now. I will admit, why is that so hard? To type multiple things and have it appear and then hit the equals and it equals out. I do admit, on the confusing scale of 1 to 10 confusing, and I'm a tech person, so remember Brian's a tech guy, I give it a 3 out of 10 confusing. The problem is Brian's a tech guy, so that means people non-techie might be a 4, 5, 6, 7. Anyways, as someone whose dad is a web designer, it feels I'm qualified to ask who the heck designed this exactly. I mean, this is much better. And why did I say Rand who maybe that's with the random number generator. I mean, the calculator, the UX aspects are non-existent. Exactly. Yep. There you go. Haslam is a good school. I was in Tickle for undergrad and starting at Haslam grad this summer, and I feel, oh, that's awesome. Well, hey, shout out to Tickle too. But I mean, I like it. I'm not gonna complain if you say we're awesome. As someone who crumbles under pressure, I think the calculator will make me cry during the exam. I wish I could contact them. Maybe I'll write them right now. Maybe I'll write them later today and be like, yo, give me your code. Let's fix your code. All it would be is like one update, and I could just make it so it shows the freaking numbers. Freaking sharks with laser beams. Okay. With that, I think there was a question about Mackenzie, let's have your dad and me work on this and just get it better. Because now how much better would this be if that said clear over there, which I could fix it. Watch this. Okay, the calculator slightly goes off the screen in the window. 2 seconds. Okay, that's not. I wish it would change the window size here. Okay. We should be able to fix it. Fix that. Also make it so it says clear or already okay. Okay, then we're gonna get serious after this. So a good way to approach SE for the mean is to maybe write the square root down. Exactly. I wish, see, it even made this better, but what I would write it down, and I do it in the video. So Josh, good question right there. Or Joshua. Good to see Griffin right there. He works for Ornell. Oh, yeah, shouts Ornell. I think we do stuff. Do we have Y12? I should go look at the board again. See if your dad knows about the business analytics program here. Well, he probably does. That's what I'm trying to point out. I'm not trying to advertise. Nothing wrong with advertising, right? But we work a lot with ORNL people, Oak Ridge National Laboratories. Shouts to all of our students who have gone over there. But ORNL, awesome stuff over there, a little over past Farragut. So good stuff right there. So his boss is a guest lecturer here, and he has this. Do you want to say who his boss is? Do you want to message me? His boss is a guest lecturer. Well, I should know. Well, wait. Give me a second. I bet I know who it is. There's a guy who is a genius, and he's our wait. And then we're gonna do one more thing. Then we'll start talking about the test. There is Haley right there, amazing. Students, all these great things. Here we go. And wait, view all faculty. Tyler's awesome. I would say, well, that's business analytics. Business analytics forum department. I would guess search. They changed this recently. It's not Ballings. Oh, why is it? It's not Nana. It's not Quick. I don't know that guy really well. Yeah, let me guess. I'm pretty sure I know who it is. I just can't remember his name, and he helped me out a lot. Everyone here is awesome, like within our department. You saw him? Oh no, I thought it was George. He does a lot of cool stuff. He's got Go at Tennessee. Dr. Me's awesome. He and I have a meeting panel. So it was someone earlier on. It was like page 1. It has to be then. Is it Jay Eccles? I don't know this guy. Is it Jay? I don't know Jay. Oh, it is? Well, dang it. I should meet him. Well, darn it. I don't know him. Well, yeah. He's super nice. We'll tell him Brian Stevens says hi. And maybe I have met him. Wonder if I have met him, and it's like, he'll be like, I've met Brian like 10 times. I'll be like, oh. Anyways. So I'd say, that's awesome. Yeah. Oh, look at this. It's like the Yeja Verity calculator, but better. You can go like 3 + 3 equals error, because I did a plus clear. Now it just says clear. And when you click the buttons, they light up. Like, not like the Yeja Verity one that doesn't light up. Because on the Yeja Verity thing, you click it and it doesn't light up. I have just remade the Yeja Verity calculator, but now. So if you're wondering how to use it, the the calculator in 0.2 seconds. It's literally. I was thinking to myself, I was like, I just make a better calculator. It's like, there you go, it's made. But with this, I know, Carson, I'm so sorry. It's so we can see what you're doing. And it'd be better for us even. Maybe I'll contact their tech support and be like, hey, look, I can fix it. So to use the memory plus buttons are kind of nice. So what you could do, if you take like the square root of something big right here, let's say you square root it. Does everyone see this? My calculator goes off the screen a little bit, so that's a bit of a problem. It's okay. You go memory plus. Now this is clear screen. Yours says A, C, and C. Memory recall. Does everyone see this? Because this is in the memory. Who's following me right here? Let me make this a part of the video. And let's just do some how to find. Okay, we're going to make this part of the video. Then we'll do the next question here. We're going to get serious. Okay, so using the Yeja Verity calculator. Okay, let's get a Word document here. So let's say we have a problem. Like, let's say it's a full confidence interval thing. And it's like y bar equals 4.3. What in the world is going on here? Y bar equals 4.3. The standard deviation equals 3.8. The sample size was equal to 45. I'm not doing easy numbers. I want to do more difficult problems. And the t statistic, the t is going to be, so if we're doing a 95% confidence interval, what is the t about equal to? This is a great question right here. Who knows if we're doing 95% confidence, what is the t about equal to? Now, we'd give it to you on the test, but with 95% confidence, what is the t about equal to? Josh, great answer right there. Now, remember, the t's a little more pushed out, so it's probably going to be about 2.0, and I'm going to go here 3. So you don't need to memorize it, and you're totally right. 1.96 is the classic z-score. So we go right here, and you'd be given this on the test. We'd enter in 95% with how many degrees of freedom? So what are my degrees of freedom on this? Great question. Nice and quick if you know it. Test questions like this, you don't need the calculator for. What are the degrees of freedom for this? This is a one sample t. That's the hint you hear. One sample t, 44 degrees of freedom. So 44 and Jesse right there, basically 2 and 44 degrees of freedom, and it's 2.02. Oh, man, I should just look at me being off by 100th right there. It's, as Jesse said, it's basically 2, because remember, the t is always further out than the z. Does that make sense? The t is always a little further out, and so we know that it's going to be a little bit more than 1.96. And if it had been something like 455, at that point, it would be 1.96 for all intents and purposes. So if you go here and do something crazy like that, it's very close to it. It approaches 1.96 as we go to higher and higher degrees of freedom. So with that in mind, we're going to go ahead and write our interval. 4.3. Oh, let's write the equation for people who don't know the equation. So y bar plus or minus the t star, which we found up there, we're trying to say it's a 95% confidence, but let's put the degrees of freedom down here. 44 degrees of freedom, comma, 0.95. That's all subscript down there. 44 degrees of freedom, 95% confidence. And now we go s over square root of n, which is called the standard error. That's the standard error, which a lot of people are worried about solving. We're going to do it on the Yeja Verity calculator here. So now we're going to go in and start solving this. It's going to be 4.3 plus or minus. And every time you do a plus or minus, you're entering into the margin of error. So I always like to solve the margin of error first, but first solve the standard error. Okay, so 3.8 divided by square root 45. So here is, as I draw my pen, here is how I would solve it. You ready? This is the absolute safest way to solve it. Has everyone seen this? We're going to do the safest way, and then we're going to do the memory way. So try solving this right now with just writing it down. See if you can do it. So the first thing we need to solve is the square root of 45. So is our page reloading? Oh, these are not amazing calculator. Okay, let me go over here. Here's our calculator. So we're going to clear the calculator. It looks like AC for you. We're going to type 45 and go square root. That's the square root. So you get 6.7, which makes sense because 7 times 7 is 49. 6.708. Or you could do 6.71. Probably fine to 2 decimals. If you feel like there's a rounding error on your test, just let us know. So now I'm going to write this in right here, 6.71, 3.8, and then I'm going to solve this, 3.8 divided by 6.71. It should be a little bit less, more than a half. So 3. Oh, we can't type on this one too. I wish we could. 3.8 divide by, oh, perfect, because that's where it's on the other one, 6.71. Now here's the issue. My calculator shows it. Very sorry. I tried to replicate the Yeja Verity calculator. When you do the divide, it's going to do it. Just hit those buttons in order, and then you should get a little bit more than a half, and it's 0.566. So this is not a perfect replication of the Yeja Verity calculator. I'm going to show the memory way of solving here in a second. Check out my other video where I use it. I guess I could try to update this one and make it worse. Yeah, right. And right here we get 2.02. And so now what you want to solve for is the margin of error. So you have 0.566. And we're just going to clear it, like pretend it's not on the screen, and do 2.02 times that's not the times. Whoops. That's where we make a mistake. 2.02 and then multiply by, how am I going crazy right here? Is there no multiple? Oh my gosh. Going crazy. 0 point, and then I'll answer your question, Carson. You got it. There we go. 1.14. So that's, and then we just add and subtract that. Can you show us examples and go into depth for type 1 type? Yeah, we do type 1 2 error next. You got it. So we would just add and subtract these numbers right here. We're going to get like 2.86 and 5.74, I believe. Double check your work, put in the numbers, make sure you got it. Here's how to use it using the memory. So you notice right here on this, it says 45. Let's go to the calculator. We'll do type 1, type 2 next. So 45 and then square root. So now I'm going to go and clear the memory. That's memory clear, and go memory plus. So now you can do memory recall. Did everyone see this? Did everyone see this steps right here? Usually 2 decimals is good, but there's leeway on them. And if you're worried, check out your exam when we show the answers. Good question, Megan, right there. But does this make, who follows my steps right here and knows how to use these buttons a little bit better now? 45 square root, memory clear, because I'm going to clear the memory, make sure there's nothing in there. And then memory plus adds it to the memory. And then I'm going to see that it's in there with memory recall. Who follows that? Like you just go, you can clear the memory, make sure there's nothing in there. 45 square root, clear memory again because I'm OCD. And then you go memory plus to add it to the memory. And then we're just going to clear the screen right here and go memory recall. And that's what's in the memory. We put that in the memory. So now when we take the number right over here, 3.8 divided by square root of 45, we can go 3.8 divide by, and then memory recall right there. And actually, my calculator might not work. Yours will, actually. So that's an issue with mine right there. So mine doesn't work perfectly like the Yeja Verity calculator. I'd say watch my video. I was trying to replicate it here, but it doesn't know the complete inner workings. I would prefer it actually pop that on the screen, but yours will actually do it right there if you do what I do in the video. So that will work, or write down your steps. If you are confused by this at all, if I would say this is not a perfect replication,
I just want to make a video showing you how to use the basic Yeja Verity calculator.
Yeja Verity video.
So if you notice at the top of the screen,
so please check out this using the actual calculator. So please check out this video right here, where I use the actual calculator right there. You can see, look at all the fun stuff in the background. It's a Joker picture. It's a Mario star. Benedict Cumberbatch. You can't even tell. That's Static Shock. It's Mario. Maybe it's Luigi. I can't even tell. Okay, so it'd be better if they updated it. I could make it better. Try to contact them. Let's talk about some type 1, type 2 error. Okay, type 1, type 2 error. 35, 43, type 1, and type 2 error. Okay, so we're going to practice. Okay, so what number is this? I know this is easy, but if you haven't heard this before, this is the way to memorize it. What number is this? What number is this? The easy part. What letter is this? What letter is this? People, I love it. What letter is this? And then we're going to say our saying. So you go like this. T. In a type 1 error, the null is true. Now think if it's true, an error is to reject it. So in a type 1 error, the null is true, but we reject it. That's the error. What number is this? What letter is this? You can do both in one response right now. Great work, good practice, just memorizing. What number is this? What letter is this? Like I'm asking this here, what letter am I making with my hand when I do this? So this is the second one. It's 2 and it's F. Joshua got it right there. So in a type 2 error, the null is false and we failed to reject it. Everyone hear the 2 Fs of the type 2? In a type 2 error, the null is false and we failed to reject it. Now here's the biggest thing. When you're doing this right here, you need to think about what is the context and what does this mean? So let's do a different example right here. Let's say, oh gosh. Let's do, I don't want to know. Let's do poker. I personal opinions with Brian. We need like personal opinions with Brian. You don't have to believe them. He just states them. I like playing poker. I think, you play a game of poker with friends and stuff like that. And, poker is a game of skill. And it's always easy to win if you have the best hands. So here is a poker game. So let's go right over here. Woo, wrong button. Here we go. I would say the null is to just fold your hands. A lot of people fold hands. A lot of you get a hand, you fold it. A lot of people do that. You get 2-7, you fold it. I like playing 2-7. No one ever expects it. And then they're like, wait, that guy plays 2-7, so then they expect it. Then you lose. And it's bad. So with this right here, 2-7 offsuit. If you know, you know. Play hand. Okay. So this is you play hand in the win. You need evidence that you should play the hand because you expect to win. If you play a hand, you're saying, I expect to win, so I need evidence to play my hand. Like aces are evidence. Does everyone get what I'm saying right here? Who follows me that you get evidence to play your hand? If you get a hand in poker, especially at a table of like 6, 7, or 8 people, you're probably going to fold. Like the most common thing to do is fold your hand. You get cards, you look at them, you fold. That's the most common thing because you didn't get good evidence to play the hand. You need evidence. You need to look around what other people are doing, what they're betting. You need evidence to stay in the hand because you don't want to. If you stay in every hand, it's probably not going to work out so well. Someone just sits and waits till they get a good flop. Flop is the 3 cards. You're playing Hold'em or Omaha. Omaha high-low. So with this in mind, what would a type 1 error be? Who can explain to me the context of a type 1 error? I need to go smaller text. What is the context of a type 1 error? So what is the context of a type 1 error? Who knows? And also, I do want to give the disclaimer. Only gamble money you're willing to lose. That goes for everything, whether it be sports betting or polling markets. I think it's important to talk about this kind of stuff because there's more and more gambling. What would be a type 1 error? Only gamble money you're willing to lose. If you're doing it for trying to make money. I think so. In a type 1 error, the null is true, but we reject it. So the null is true. Yeah, I think people are saying it. Exactly. The null is true. And that's the great thing because even I had to slow down. I'd be like, wait. It is true that we should fold. We should fold our cards. Here's the thing. You might be like, I just got aces. I just got pocket aces. Ace of club and ace of spade. There we go. Ace of spade. Can't sing it. No AC/DC. And so the null is true, but we reject it. We say we shouldn't fold. We stay in and we play. And we lose. A person plays their hand, but they should have folded. Exactly. The null is true. We should have folded. And you wouldn't know it. You're like, I made a type 1 error. I thought it was a good job to play aces. And you might say, but it's good to... Just depends. I don't know. It depends. Playing aces against like 8 people heads up. I don't know if you'd have a more than 50% chance to win. Or the worst thing, the worst hand for someone else to have the worst hand for someone else to have on that table is going to be pocket aces. And then if there were other people, like, this would be horrific for your table. Because if you think about this, if you play a table with, like, I would bet if somebody down here had 2-7 same suit, they might have an edge on this table. It just depends. They'd have the most unique hand, and they'd have the best chance at a flush. They can't get a straight, though. So if you had, like, 5-6 suited, it actually probably might edge out. You'd edge out the kings probably because the aces are going to have the aces are going to start out winning, but no one can get the aces can't get no, they could get a low straight. You're also eating into this anyways. Poker. Okay. That's what a type 1 I love poker. It's all math. It's all thinking through it. What would a type 2 error be? I think you see it in a type 2 error. The null is false, but we failed to reject it. And this might be the 5-6. This might be the 5-6. The null is false. So it's false that you should fold, but you retain the null. You fail to reject it, so you keep with it. Does that make sense right here? You don't reject the null. So the null is false. You shouldn't fold your cards. That's what it means the null is false. It's false that you should fold, but you stay your cards. You fold your cards. Yeah. Yeah. They should have played the hand. Exactly. And a type 2 error, the null is false, but you fail to reject it. So you, you fold your cards, but you shouldn't have folded. It's false that you should fold your cards. So you should have played and won that. It's like when you're like, oh, I would have won that hand. Like the flop hits and it's like, it's the remaining 5s and you're like, no way. I would have had quad 5s. You're like, ugh, type 2 error. Exactly. Good to see you, DD. And so a type 2 error, then all is false, so we fail to reject it. He'll do another one. And here, does anyone have another context we could do? And I might try to see. We got some study fuel for business analytics majors on our floor. I might try to take a little study fuel. I need some study fuel. The null, what would be the null? Let's say 5-2. Yeah, of course. We'll do that. I'm gonna do this problem, then I'm gonna maybe check out the food a little bit, give a little snack, and wait to buy car. Wait to buy TV. This is Brian's life choices. I'm currently So one of my issues, Brian's about to talk about life here for a second, is that apparently there's more intrusive ads on things. Like you turn on your TV and it's like, hey, would you like to buy some fabric softener via Amazon? I'm like, why are you putting an ad on my TV? I don't want that. I'll go back to tube TVs if you do this to me. So the null is to wait to buy a TV. You shouldn't just buy a TV randomly. You don't just buy TVs. You need evidence to buy a TV. And at some point, you're welcome, Carson, right there. I will put more videos into this because I need evidence to go buy a TV. So evidence is a good thing to remember, is always for the alternative. You need evidence to buy TV. Like, you're not just going to buy TVs every day till you have evidence. Like, an evidence would be your TV's broken. Evidence would be maybe you want to buy a TV before they start putting intrusive ads into them. So you get evidence and then you buy the TV because you have evidence. You usually go through your day not buying TVs. I do that. Maybe you don't. So with this in mind, what would be a type 2 error? Who can explain to me the context of a type 2? Now you have to look and say the null is false. It's false that we should wait to buy a TV. That's a false statement. If someone says wait to buy a TV, they just told you a lie. It's a lie. But think, if it's false that you should wait to buy a TV, what does that mean? It means you should buy a TV. Don't just buy TVs. So what does this mean in context? Wait to buy a TV, although they should have bought. Exactly. It's like next year, it's all like intrusive ads and you can't get the old ones. The old ones go up in price. Everyone's like, oh, now the old ones cost more because everyone wants the TV that like doesn't do this. It doesn't be like, please watch this 1-minute ad while your TV boots. I really think we could be going towards that future. I'm like, if my TV were to be like, wait, while your TV loads, it's like, you got to be kidding me. I mean, especially like cloud computing, everything, really replace TV with computer parts. Exactly. It's like a TV. I just need, you make screen, you put, I don't know, panel, has a board in it. Board, yeah, get it. All right, so then type 1 error, we know it. Type 1 error is the null is false. Wait, in a type 1 error, the null is true, but we reject it. So the null is true. I like to do green for true. The null is true. We should wait to buy a TV. So imagine this. This is the classic, like you buy a TV and then it's on sale like a week later and the store's like, too bad. You bought it for 1,000 and now it's 600. Well, I mean, TVs nowadays you can get for 600-700. I got with this in mind, you buy the you reject the null, but the null is true. You should wait to buy a TV, but you reject that and you buy the TV. So in a type 1 error, the null is true. I'm sorry, DD. I've done it. Well, I'm going to be right back here. I'm going to see if there's a little bit of food. Be right back. Bye from everyone. We'll be back in like 5 minutes. Bye. Okay, we got a practice problem right here. And please ask more questions. Going to keep streaming while there's questions. I do have to go, but eventually we got another, like, I don't know, close to an hour left. Who knows? Let's take this question right here. It is practice problem on confidence intervals. So confidence interval practice problem. Now, what I like to do whenever I get a problem is immediately go to the formula sheet. So I'm not going to read everything yet. I'm just going to look at this and be like, what are we doing? The American Banking Association is concerned about the percentage of customers who default on their auto loans is too high. They are basing this on a 95% confidence interval for the population proportion. So go to the formula sheet right here. Mubot's got in the chat right now. But does everyone see this? We have the link. And then if you go to the formula sheet, what is the very start to the equation we're using? So tell me the very first start to the equation we're using. What is remaining a confidence interval for the true proportion? That's what it said. Does anyone know is it like TDF? What is the very first start to what we're doing? The very first, just read me the first part of it. You don't have to read the full thing, but can you find the equation? It's the p hat one. Great job, Megan, right there. It's p hat plus or minus z star means based on level of confidence. The standard error is right there, p hat times q hat over n square root. So it asks what is the margin of error, and this is where people usually get a little bit confused, because when it asks about the margin of error is a conceptual idea too. Because the margin of error, if we have the interval from lower, which is down there, to upper, so lower is here, and the upper is here, then the margin of error, which we're looking for, which it wants the margin of error, is half the length of the interval. So the margin of error is half the length, and so we'll go right here, and this is called the center of the interval. And so how would we get this? Well, we would do the formula upper minus lower. And you notice that gets you the full length. That gets you this right there, the full length. And then we divide by 2, because that's the distance they are apart. And all we do is plug in the numbers here. Upper minus lower divided by 2. So upper minus lower, there's the distance they are apart. And make sure it makes sense right there. They're about 0.07 apart. And divide by 2, and we get the following, 0.0349. Now, the next one uses the same ideas, but think about this. If we know that this is plus 0.0349 and this is minus 0.0349, and we know the lower is down here, tell me if you get where I'm going with this, Megan, or Joshua in the chat. We're going to figure out how to get the center of the interval, because we have a margin of error right now, and then we have a lower bound, and we have an upper bound. So how could we get the how could we get the center of the interval? So the upper bound is at 0.2329. So what could we do? As it says, what is the sample proportion? Because the sample proportion is the center of the interval, because it's p hat plus or minus the margin of error. Does that make sense? With the color coding, it is x over n. You are correct. But also, the center of the interval is p hat. Because does this make sense right here? Because p hat is the center of the interval. And so with this is a conceptual question. Like, it's a little bit like, we don't actually give you x over n, because p hat, which is x over n when you find it, is the center of the interval. And the interval can be written p hat plus or minus a margin of error. Now, the margin of error, if we go into more detail, the interval would be p hat and then plus or minus the z star standard. I was writing standard error, and then I meant to do p hat q hat over n square root. So this is the same equation written over here on the side, but I just abbreviated it to margin of error. Does that make sense, Megan, right there? And so what could you actually do right here? Well, p hat is the center of the interval. So when you're doing this right here, what is the sample proportion? Well, it's just at the center. So you could take the two numbers and average them. So you could do upper plus lower, divide by 2, and that gets you the center of the interval. Does that? Exactly. Nice job. You were figuring out as I was saying it. Good work. And so you could just add the two numbers. You could also add a margin of error to it. So you could go down here to the lower part of the interval and add 0.349. And that should be the center. You could also confirm by doing the following. you could go right here and do upper or lower plus upper. You can add together whatever you want. And then divide by 2 and 0.198. So that should be right. Point equals 0.198. And you can then confirm your answer by subtracting a margin of error, because if we add the margin of error to it, 0.0349, we get the upper bound. Notice that right there. If you subtract the margin of error, 0.0349, you should get the lower bound. So the formula for the confidence interval is the center plus the critical value times the standard error. That is correct. And we see that in a lot of other formulas here. No, that is correct, Megan. You've done it correctly, because p hat plus or minus z star, and then the standard error is this portion here. Let's make it clear. So every interval we write has the following format. And I'm going to make it a little bit bigger so we can see it better. The start of the interval is the estimate, or the center of it, and then confidence level, and then everything from here over is margin of error. So margin of error. And we could, I guess, do this. Right. You know what? Let's do this on a new sheet. So let's go right here and do this. And do this. And then here. Okay. So this is the estimate, which is the center of the interval. And this is the margin of error portion. And the margin of error is made up of the confidence level. And it's also made up of the standard error. Sorry, there you go. I think that's readable, standard error. So that's all part of the margin of error. Does that make sense? It has component 1 and component 2 right there, and the center is just the estimate. So when you write an interval right here, you'd have something like p hat is your estimate. And then I guess we could put over here truth we're trying to estimate. So let's do this. That's not part of it, so I'm going to put over here the truth of what we're trying to understand. So if we're trying to estimate p, we would use p hat. So does that make sense? Stop me if I'm saying anything confusing. I'm doing the intervals in green. And then the margin of error starts with plus or minus z star, which means you pick it based on level of confidence. And then p hat times q hat over n square root. So does that make sense right there, Megan? So there is one of our intervals. The other interval is going to be for estimating the mean, which is mu. And our best estimate of the mean is the sample mean, because we're trying to estimate the truth, plus or minus t star with n minus 1 degrees of freedom, s over square root of n. And then the last interval is trying to estimate, move a little bit closer to me, it's trying to estimate mu1 minus mu2. And our best guess of that is going to be y bar 1 minus y bar 2, because we use the sample difference as the best estimate. And this is t star with complicated degrees of freedom. Too complicated. My D's look like O's. I can't write. There we go. I'll learn how to write eventually. And then the standard error formula is square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. But how does this look, Megan, right here? This is my little cheat sheet to try to help you understand. And then I guess we could go here and put lines between them to make it clear. Hopefully there we go. Almost. Yeah, good. I'm glad that's what I want to do. I want to be like helpful on these things, so that way people can understand and see where they're at. Okay. And this one I can go right here and do this. But there you are. There's your different intervals. S over square root of n. So there's the truth is what we're trying to estimate. When you make an interval from p hat, you're trying to understand the true proportion. The sample proportion tries to understand the true proportion. It would give you the z star, t star, exactly. And there's classic ones. We could talk about this real briefly right here. But the most classic z's or t's to use. Here we'll put this small table right here. So z star is constant. And the way it goes is when you go from we'll make a small table right here. Z star, we'll do it. There you go, good. And then we'll go down like this. So we'll go confidence level. If you have, let's say, 68% confidence, it's basically 1. With 80% confidence, it's 1.2816. With 90%, you do not need to memorize these. It's 1.645. What do you notice as you get more confident? The Z gets water. As you get more confidence, the Z gets water. As you get more confident, the Z gets water. It gets bigger, exactly. Which, when you think about this, it's going to make the interval wider. When you're more confident, the interval gets wider. Or we could, because we can put our classic one on here. We can go all the way down to a number you should know. And I want you to tell me this last one right here. Tell me the last one. If you're 99.7% confident, technically there's a 3. That's a hint. But if you're 99.7% confident, what would the Z score be? If you're 99.7% confidence, the Z score would be what? Because 68, 95, 99.7, and this is technically 68.26, and then, yeah, it'd be 3, yeah. So it just gets wider and wider, and it goes to the percent of area you're covering on the curve, such as like 1.96 from negative to positive is the middle 95% of the curve being covered right here. It's the middle 95. So that's what these represent, is the middle 95%. So 1.96 is what you would use right there. But if you go further out, you cover more and more of the curve. So you could see right here, if we were to build like a 98% confidence interval, you'd have to go further out on the bounds of what you're doing right here. So a 98% would be, you'd go further out and cover 98% of the curve, and you'd go to 2.3263 and positive 2.3263. So that would cover the middle 98% of possibilities right there. Any questions about this? And I could talk about the T slightly, but so a good way, right, as the test started. You could, the margin of error as upper, you could, I mean, those are just some classic formulas to know. So we could write that on this little cheat sheet we're making, is that we could write the formulas that we just talked about, that the center is equal to the upper plus the lower divided by 2. You average the numbers. And then the margin of error is equal to the upper minus the lower, oh my gosh, I can't write a WJ, divided by 2. You think about these equations, the center is just the average of the two values. So when you find the center of the interval, the center is just going to be the average of the two values, and the margin of error is half the length of the interval. Does that make sense, Joshua, conceptually? That when you find the center, adding two numbers and dividing by, average them. Do you follow me with that? Like, this is what that equation is doing. Where the other equation is asking, how far apart are these numbers? And then taking half the distance. So you're taking half the distance. You're dividing it in half to make a plus or minus. So that's not a minus. But just conceptually, it helps to know. And then you can just rewrite the formulas, because you're like, oh, the margin of error is half the length of the interval. Here's the length of the interval. Here's half the length. So if you take the length and cut it in half, you get a margin of error. Or the other one, we'll repeat it again, is the idea of the center of the interval is just averaging two numbers. Add together two numbers, divide by 2, tells you what they average to, which is the center of the interval. So just some good stuff right here. And I would say try writing this all down. I know it helps when I write it down, but I tell you, I've learned these things over multiple years, just trying to, draw these things for myself. But I'd say this is a pretty good cheat sheet right here of, what is the idea of like a 98% confidence interval. Comes from the Z-score relative to the percent of area we cover on the curve. And we didn't mention the T, but we could go in detail. Snoozer, good to see you there. What other questions are there? What should we talk about? You name the question, we do the question. Oh, man. What should the question be? Make sure. I'll look at that later. Is there anything you would say is more on the test? It's pretty even, I'd say. Good question right there. Chi-squared. Chi-squared. Everyone wants the chi-squared. Sometimes I like do accents. I'm like, what accent am I doing? I don't even know. Don't ask me. I just do them. They're filling the robots outside with food. If you put food in a robot, are you feeding a robot? Probably not. Robots don't need feeding. At least I don't think so. Okay, chi-squared practice problem. We're going to try to cover all the ideas of chi-squared by doing this right here. So first off, when do we do the chi-squared? Who knows when we do the chi-squared? When we can do the chi-squared. There's actually other statistical techniques you can use, but when do we do the chi-squared? So first question is, when do we do the chi-squared? Exactly. And that's actually, so the answer is when we have two categorical variables and we want to investigate if there is a relationship between the two of them. And this actually leads to condition counted data. So you can't do the chi-squared unless you have two categorical variables. So very important right there. And we are testing for the independence, which actually that's great. What is the null? And alternative. So the easiest way to say the null, more mathy version of a mosaic plot comparison. Yeah, we'll do that coming up here. We'll do some of the, we're gonna go in and keep going through, Joshua, you got it. And we'll do some mathy versions. The null is independent, right? So X and Y are independent. And another way of saying this, X and Y have no relationship. So they have no relationship. X and Y are not associated. So that's just three ways to say it right there. So now what is, oh wait, we did was the null. Okay. What is the alternative? There's not multiple alternatives, and Austin's doing it right there. It's just the idea of like, you could literally say it like X and Y are dependent. Pearson gets a little mad at that, but you can do that. X and Y are not independent. X and Y are associated. X and Y are related. So there's a lot of ways to say it right here. Just remember, like, if you say they're not independent of each other, you're saying they have some sort of relationship. Very important to see what's going on right here. But just notice that the null, the easiest way, it's the chi-squared test of independence. The null is that they're independent, which means it doesn't matter. Rock knows. It doesn't matter. Rock going to be here tonight? Probably not. I don't know. I don't think it does W anymore. So let me ask you this. We'll do the conditions right here too. We're going to do all the conditions. So let's start with this. Let's say we are going to look at version A and version B of a test. And we want to see, do students pass or fail the test? Does that make sense? Which of these looks more in line with the null? So I want to know which of these two graphics, these mosaic plots, looks more expected given the null is true. So we're going to have version B is going to be an alternate version of the test, so less students will take it. Notice the marginal display with less students taking it, because the width of this shows how many students took it. So version B had less students versus version A in both these examples. It's like World 1, World 2. Now, we're going to look at the percent who pass. We're going to put pass down here at the bottom, and then we'll put fail up at the top. I forget I have an eraser on this till I touch it. And here is the results of World 1. And here's the results of World 2. Which of these, World 1 or World 2, looks more in line with the null? Which of these looks more, and remember what the null is. We'll repeat what the null is in a moment. I wish I could just click fill shape. Correct. World 1 looks more in line with the null. And let's explain why. What is the null with version of test and passing or failing here? What is the null? So who wants to say what the null is? Just tell me what the null is. And the easy thing to do is, remember, just write the word independent between them. So we have here, we have version of test and passing. So what would the null be? The null would be what? The null would be what? The null would be what? Just tell me what the null is. You can see up here we've got And all I have to do is put the word between them. The null would be what? The version is independent of passing the test. And that means it doesn't matter, right? That means whatever version you get, about the same. And these differences right here, you know how we say the differences are likely by random chance? These differences look like they could be by random chance, like just visually. These look unlikely by random chance. We don't have a p-value yet, but does that make sense when I say like the differences we see here between version A and version B are unlikely by random chance? That's what a p-value tells us. It quantifies the probability of seeing this difference. Do you want to have like an O moment where you're like, whoa, that's what the p-value's doing? It's quantifying how big this difference is and how likely it would to occur if there really is no difference, because the null assumes there's no difference there. Austin, I like that. End of class, let's get those epiphanies. You understand what a p-value is? You're like, whoa, it's telling us how likely. Yeah, I get it. So this would be the one that is unlikely by random chance, and that one's more likely by random chance. So one has a high p-value exactly way above alpha, and the second one likely has a low p-value. I agree. And so now let's do this result right here. Let's run this. You ready? Let's run the test, and let's look at a table. We're going to pretend we have the world 2 results, and we're going to even do all the conditions. Okay. So version B was actually because we ran out of paper, which means the students who got it are completely... So we ran out of paper, and we had to print new versions, and we printed the wrong version. So this is not what happened or anything. it's a fake story. But now we're going to look at this right here, and we're going to look at the table. So here's our table for it. And let's put in the results. And version A, version B, and version B had 100 students take, 500 students took version A, 600 total. The students who passed, let me think. This is pass. This is fail. So we saw of version B, we saw, you know, I'm going to do something right here because I want to do this. Trying to make it visually accurate. Okay. 4 students passed version B, which now I can solve everything. 96 and failed. And then up here, we need, well, we don't have the totals. So the amount who failed, 96, and there's not that many more. Let's go 120 failed. And so with 120 failing, this would be 24, and this would be 476. Okay. So now let's check our conditions. Let's check our conditions. Condition 1, these tests were given out, Whatley. Condition 1, these tests were given out, Whatley. The problem is if it's a makeup test, then there could be differences among the students. So you got to watch out. Like maybe you want to give it randomly. Mubot loves some randomness right there. So did we randomly give this test to students? And this is what we are going to see on a test. Yes, this is the expectation to solve certain things, trying to mimic as best I can the test. Usually the questions are smaller. It's not like a full, like, solve this 1-page chi-squared. But if we do it, we'll hit all the different versions of what you might see. A lot of them. Not all, but a lot. And then we'll try to find some numbers here in a second. So now condition 2 is what? Condition 2 is what? Which I think we've met. Condition 1 is random. Condition 2 is what? What is condition 2? Condition 2 is what? Less than 10% of the population is sampled. And since this is like giving a stat to 1 test, we could probably say there's near infinite students who could take the stat to 1 test because we get more and more each semester. So you might say we're probably good on that. We won't worry so much about it, but it means less than 10% of the population is sampled. Now we pause, and what is condition 3? Now we pause, and what is condition 3? We pause, and what is condition 3? I'm going to do something right here while you tell me, really. Expected cell count. Expected cell count. It's expected cell count for the chi-squared. The success failure is for proportion data, and the nearly normal is for quantitative data. So what I did right here is I took this, and let's find one expected cell count. which one of these would be the best which one of these would be the best expected cell count to check? Like, I always tell you, if you want to check it really fast, check the which one. Which one of these would be the best one to check? B fail, exactly, because it's the smallest. If you do the smallest row and the smallest column. So remember the trick for it? It's row total times column total over grand total equals expected cell count. You just circle the cells that you want, you divide by that, and they cross in on where they meet. Does that make sense? Row total times column total over grand total. And so 100 times that, it should be my brain, slowing down. It should be not 200, 20, it should be 20? Maybe 20. So 100 times 120 divided by 600, 20. I was right. So it's 20. Now here's a fun fact. Since this is 20, what does the cell above it need to be? Since this is 20, now you could find it. You can just do the math. If you want to do the math, well, that's not going to do it now. You could just do the math. But what's our trick? Does anyone know the trick? You can do that math right there and find it. But what's the cell above it have to be? It has to be this. There's reasons that we'll talk about in a second. Go ahead and solve the math if you want, and I'll tell you the trick. I'm still on top chat. Has to be 100. Mm-hmm. Hey, Grace, good to see you there. It has to be 100 because of the degrees of freedom. And how many degrees of freedom does this have? It only has 1 degrees of freedom because this is a 2 by 2 equals 1 times 1, because degrees of freedom are rows minus 1 times columns minus 1 equals 1 degree of freedom. So there's 1 degree of freedom. So because of that, it has to equal the totals exactly. You can go through and solve each one of these individually, but does that make sense, Austin? It's like a quick thing. You can be like, well, and you can actually do this on the test sometimes too, because you might be like, well, it's a forced choice if we give you other expected cell counts. We don't usually make you solve a lot of them. We usually say, like, fill out this like, we give a few spots and we have you solve some of them, but we don't make you usually solve all the degrees of freedom. So we don't make you solve all of it. So what does the degrees of freedom have to do with that? The degrees of freedom show us the chi-squared shape. More on that in a moment. But does that make sense, Austin, right here? The degrees of freedom are rows minus 1 times columns minus 1. So rows minus 1 times columns minus 1 equals the degrees of freedom. Not multiple. It's kind of like Canvas content where it's multiple choice. There's numeric entry. There's not fill in the blank. Well, there's not like written questions, but yeah, good questions. And so with this in mind right here, do we pass the expected cell count condition? Do we? So we only have 4 people right here. Do we pass the expected cell count condition? Yes or no? Who wants to say yes or no? Do we pass? Because we only got 4 people right here. Yes. I was trying to trick you. Don't worry if you got tricked. The answer is yes, because it's the expected cell counts, and there's at least 5 for all of these. And the one that really mattered was the 4 is observed, not expected, because that's the observed, which is what you see, or the count data. So what's the last condition right here? What is the last condition? We just did random data. Less than 10% of the population is sampled. We have at least 5 expected cell counts. You can see right there, all the expected cell counts were greater than 5. What is the last condition? The last condition, which you might check first. It's not bad to check first. It's pretty easy to check. We talked about it a moment ago. It's counted data. And do we pass that? Yes, we do, because both variables are categorical. So counted data means, or count data, either which way, Rock knows. It doesn't matter. Counted data is going to be that both variables are categorical, and we do pass that. So now we're actually going to start to run the test here in the background. So now we need to do the test. Okay. So now we need to figure out all of the cell chi-squareds. Exactly. So basically CC, not QQ anymore, CC. So now the cell chi-squareds is going to equal the observed minus the expected squared, quantity squared, over the expected. Make this a little bit bigger here so we can write it in. There we go. And so the observed, I think I put 400. So 400. Wait, that's what we expect. 476. Okay. Observed 476 minus 400. Can I do it? That's good enough. Minus 400. And over expected 400. Observed right here would be 24 minus 100 squared over 100. And if anyone wants to help me find these, that'd be awesome. And then the expected down here should be 20 and 96. I don't think I made an error. I hope I haven't. There we go. And then this should be 80 for this. And only 4? Did I only put 4 in there? I did. Yeah, I remember that now. That was my trick. I forgot about it. 4 minus that equals this over 80. And remember, this number right here, that is coming from the expected, which is the numbers all in here. Does that make sense? Oh, nice. Top left is 14.4. Thank you, Megan, right there. And then the other number, like this number right here, do people get where these numbers are coming from? I'm trying to highlight so you can see are the observed. And we might go back and screen out so you can see it. But the observed are going to be right here, as long as I haven't made a typo. But you can see where I'm taking the numbers from the expected in blue versus the observed. So there's all the observed minus expected squared over expected, and we zoomed out a bit so you can see where the numbers were taken from. We defined all of our expecteds, and Megan's found one for us right now, or the chi-squareds. So the top left is 14.4. And top right is nice. Wow, that's huge. Wow. I can already tell you the p-value on this. I can tell you the p-value. And so let's get the bottom left now. 4 minus 80, quantity squared, divided by 80, 72.2. Oh my gosh, I'm going to break everything. 72.2. And then the last one is 96 minus 20, quantity squared. This is going to be even bigger than. Woo, 288.8. Oh my gosh. I hope if I didn't. Wow. Okay, so what do we do with all the cell chi-squareds here? So once you want to get the chi-squared test statistic equals the what? Tell me a 3-letter word. Because you take all these. This is the Pearson chi-squared test statistic. The Pearson chi-squared equals the sum of all the cell chi-squareds. Does that make sense? You have to take all the cell chi-squareds and you sum them up. So you sum up all the cell chi-squareds, the sum of all the cell chi-squareds. And don't use the applet if you know, you know. What is the p-value? Does anyone know the p-value of this? 433. Wow. Oh, nice. Great job, Megan. And wow, nice. Everybody. So what is the p-value? Well, here's what our distribution looks like. I ran out of room here. That's a bummer. Yeah, there we go. Our distribution looks like, not like this. Then we wouldn't ask on the test. The test would, this is a question we can't ask. But the chi-squared with how many degrees of freedom? 1. And it's going to be, it's basically 0. Because the curve looks like this right here, and it stops at about 10. So we are over here off the curve like ridiculously. Who follows me that we are like way off the curve? The curve, like if you looked at it, it wouldn't even be visible over here at 433.2. And the p-value is going to be this area to the end of beyond this curve, which is nothing. So, and we can go view this. Good to see you, Caroline, right there. We could go view this on the chi-squared applet, but we are so far off the curve. 1 degree of freedom was found by doing rows minus 1 times columns minus 1. It is a 2 by 2, so there's 1 degree of freedom. And we're going to go over here to the applet, which we wouldn't expect to use on the test. But here is the chi-squared with 1 degree of freedom. As I said, it looks like this, extremely right skewed. And then we type in the area above, and we find p-value. Find p-value using chi-squared. 1 degree of freedom, 433.2. 0.2, and we'd have to enter in a lot of decimals. Like the applet won't even find it. It's so small. If you didn't see right there, I broke the applet, but the p-value is infinitesimally small. I might be able to use R to find it. So is it Q chi? Q chi squared. There we go. I always get I think it's p chi actually. Okay. So above something, let's do above like 4 with 1 degree of freedom. It's not right. It should be Q chi. No, I guess it is p chi. Is it doing a left tail? I think it's doing a left tail. Because we enter in like 9, it should be close. Yeah, it's doing a left tail. So we can do 1 minus. That'll do the right tail. All right, so now 433.2. It's going to say 0. That's what I thought. But let me do this and do options, digits, equals, none. Oh, 22. Oh, SciPen. Options, mess up my R here. SciPen 99. It's about as 0 can get. Maybe ChatGPT, but it's way towards 0. I don't even know if I had 200 if anything beyond it. Yeah, what this tells you is that the differences you are observing right here, there we go. Now you can actually see it, but it's gonna, at that point it goes 0. It's telling you that these differences you observe between the two tests are virtually what? Think of an I word. The differences between these tests, which are obvious, hence virtually what? To occur by random chance. The p-value is basically 0, telling you that these differences we observed are virtually what? And then what would you conclude? What would you conclude? What's your result here? What do you conclude? What do you say? What's your result? The differences between the two tests are virtually impossible, exactly. And we wouldn't have you find the exact one on the test. Yeah, we can't. There's just not ways. Think about the way we do on Canvas content. There's no real way to do it without you using applets. So we can't. I don't know. Maybe one of these days we need to print off tables again. Like, because we keep thinking of different ways to test. Conclusion, differences of the scores across the versions are not independent. Exactly. We have evidence of a strong relationship. Perfect answers right there, Austin and Joshua. We have evidence of a strong relationship that they're not independent. Like, the test you took is not independent of passing and failing. There's a strong evidence because the p-value is well below the alpha level. What is our traditional alpha level? What is a traditional alpha level? Alpha is the point at which you reject the null. It's also your type 1 error, 0.05 classic, because it relates to the 95% confidence interval. Well, the question that asked you to solve for a p, there's just not really good ways to do it. A lot of times we go for interpreting the p-value, so we don't have a lot of like solve, nothing that would require an applet. A lot of times questions ask theory questions about p-values, like would you reject the null? We have you look at results of a test and say, what is your conclusion at this alpha level? So here, we'll do a little p-value theory. You ready? Let's do a p-value theory part of this review. P-value theory, gonna talk about. So p-value theory question. P-value theory practice. Okay. So with this, so are there applet photos? What we could do is, let me do this. I'm gonna do this. Okay, we're gonna do output you've never seen. But I want us to think about this. You ready? You've never seen this output. I want you to check this out. Here is data from, oh, I haven't loaded up my libraries. Library, reg class, data, survey 10. Okay, so I'm going to look at the association between, let's say, somebody's height and their gender. Does that make sense? Who follows me on this? We're going to look at the association between height and gender. What is this graphic called? Be very careful with its name. What is it called up there? What is this graphic called up on the top right? That graphic is called what? It's basically box plots. It's basically side-by-side box plots. It's box plots, plural. It's side-by-side box plots. The visualization of two categorical X and quantitative Y side-by-side box plots right down there. And don't worry, it's box plots, but two of them side-by-side. So this would be a 2-sample T. You're exactly right. So, and great work, right? I wish we could throw more MuBot points, but we stopped giving them out. MuBot, thanks you. But not with points today. This is a 2-sample T because we're looking at the what between the heights of men and women. We're looking at the what between the heights of men and women. In the 2-sample T, we analyze the mean, and we look at the difference. See, Austin, have a great summer too. Can't believe it's summer, man. We look at the difference. And let's take a look right here. Here's the output. The average male reports to be 5'11.3. That's 5'11 right there. The average female reports to be basically 5'5. The difference between them is almost 7 inches. 6'7". Are we going to have an extra time when doing problems with the use of Verity calculator? It takes even longer. There's the 90 minutes right there, David. And then check out the practice right now we have open. And also I made a video on it showing how to use the calculator. We did a little start here too. And I might even try to make, maybe I'll end early and I might try to, I'm really trying to make a version of it that you could practice with more, but we have the practice test open. That might be best because if mine's not perfectly like it, I don't want you practicing with it. Because I did earlier make a faux Yeja Verity calculator, just so you can see real quick. We were talking about it during the start of this review, but I made my own, but my own is better because you can go look at that. I know yours doesn't, but mine actually shows it. I'm gonna try to reach out to them and say, hey, you want me to tell you how to update your calculator? So we could do that. And mine even says clear right there. So when you clear it, my buttons blink. What? Yeah, there we go. But definitely, and the questions aren't that long too, so that's a good plus right there. But check out the start of the video. We talk about the Yeja Verity calculator. So with this right here, nice, yeah. And then, but also Joshua, check out our practice thing. Open up the practice. It's got the calculator on it. So go check that out on Canvas, and that will allow you to take a look at it. So you can see it before the econ too. So Megan, what about this p-value here when we look at the averages? When you look at the averages right here, what does that p-value tell you? Because remember, we're comparing the differences between the means. So what would this p-value tell you? What would this p-value tell you? The differences in the averages are statistically significant. So these differences we see between females and males are not likely by random chance. You can do it for anything. You can do GPA and run it. This is why I love doing statistical tests. Notice how this is a smaller difference. The difference right here is only about 0.2 of a point, but it's still a statistically significant difference between average. We could do, let's find one that's not significant. So we're going to attach the Survey 10 data. And let's go here, names of them. So I love coding. How often do people use Facebook? Hopefully we find something not significant. No, Facebook usage is significantly different. How intelligent you think you are. Oh, man. Nope. Males think they're more intelligent. True, who knows? How attractive you think you are. Who thinks they're more attractive than... Let's find out the answer. Gosh, what is... I find this interesting. What am I seeing? Megan, do you see what I'm seeing? I'm like, well, that's interesting. What are you noticing right here? What do you notice? This is percent people think they're more attractive than. Do you see what I keep seeing? Where I see this and this, and it's like, well, would you look at that? It's funny because I hear people saying like I've heard supposedly. It's empty. For supposedly that men are, but how, if this is the percent of people you're more attractive than, then it has to be, if you talk to everybody, it would have to average to 50% if everyone gave an honest answer. It would have to be, because everyone can't be more attractive than everyone, or that doesn't work out mathematically. So this answer is more in line, closer to the 50%, than this one closer to the 50%. So I find that interesting. I'd like, oh, look at that. And percent more athletic. Guys are going to think they're athletic, right? Right? Yeah, 20 points, almost 20 points. Men think they're way more athletic. And let's look at one. We're trying to find something that is not how funny they are. Did we do funny? I can't remember. I feel like that's the one we didn't do. Yeah, men think they're funnier. Men think they're attractive. Gaming. Well, here we'll just look for gaming, but I feel like females on average an hour, men on average 4.2. Saw this. Yes, Briley. I wish we could throw you some points. Wait.
Statue 1 legend, Briley, thank you for swinging by. Shout outs to you, the club, and everyone. Woohoo! Finals week.
Shout from Ubot. Good to see Briley in the chat. I'm trying to find something not statistically significant. Everything is statistically significant. Everything is. Maybe tattoos. Do men and women get a different amount of tattoos? Do they differ in their tattoos? Oh, it's because we had a lack of... It's because of one of the tests couldn't run. And thank you for clicking on it, bro. That means it actually advertises more to people. How many phone contacts do you have? Who's more social? We found something not statistically significant. We finally did it. And look, the difference is a lot smaller. It's only a difference of about 6, 7. I am not doing this on purpose. You don't trust me on this? It did it to troll me. It's only about 6 or 7 phone contacts, really. And with that in mind, seems on purpose. Sorry, David, right there. Totally, I did these examples beforehand. On the exam, should we assume the alpha is 0.05 unless otherwise stated correct? You wouldn't use like a 0.60 alpha here or something ridiculous. And you know what we can do? Watch this. We can look at significant other. And we can see, does someone's gender... Oof. Okay, wait. I need to change the SciPen on this. Digits, 7. SciPen, 7. And there we go. That's much better. Does someone's gender, is it associated with having a significant other? Who is more likely to be dating according to the data? Everyone take a look at the data right here. Men or women, who is more likely to be dating? Who is more likely? Well, men, I thought you were so attractive, so funny, so athletic. Sorry, women right there. It's just, I like messing with the data. I'm a guy, so I get to say these things, right? I'm the reason the GPAs are lower. It's not good. So right here, you can see women are more likely to be dating. And are these differences statistically significant? The answer is yes. Because if you take a look right here, here is the p-value. Does everyone see this p-value right here? The p-value tells us that the null hypothesis of gender is independent of having a significant other can be rejected. That there is some sort of association between gender and having a significant other because the p-value is low, so we reject the null. And we even do things in this output like get confidence intervals for p-values to say I'm 95% confident the true p-value is contained in the interval there to there. You can see you get the count of observations, you get the table of expected counts, and then you get the percentages across the conditional distributions. This is a different type of output right here, but it doesn't hurt to see it, to understand it. What other questions are there? Maybe we'll take 1 or 2 more questions, but what other questions are there? How can you drink energy drinks and be falling asleep? How can you? Let's see. Conditions for different... Yeah. So let's do the conditions for the 2 sample means. The conditions for the 2 sample means. Okay. Oh, thank you right there, Hayden. I appreciate it. It's classic Nightwing. Some Dick Grayson, right? I think so. Flying Grayson. No. Wait, Tim Drake, Dick Grayson. Oh, and Damien. All the Robins. What's her name? She became the spoiler, right? Or something, right? I don't know. Let's do the conditions. Anytime we do the conditions, condition 1 is going to be random. And I need to go right here. Actually, let's go new RMD, our markdown file. 1 second right here. So new markdown file. That way I can type inside of here. And actually, you'll see in a second. Visual. Okay. So you can use, if you ever try to use RStudio, you can use it, maybe eventually, as a Word document creator. And it's loading up. There we go. So the conditions. Condition 1, random. Condition 2, 10%. Less than 10% of the population is sampled. Now, what do we do before we say condition 3? What do we do before we say condition 3? Pause. So we always pause right here. It's not a condition, but you stop and you say to yourself, not myself, but yourself, you say, what am I doing? Why am I here? And the answer is to do all the conditions for the test. So it really depends if you are doing, here we'll write 3 for categorical, or 3 for proportions, is going to be success/failure. 3 for means is going to be nearly normal. And then 3 for chi-squared is going to be the expected cell count. And 4 for 2 means is going to be independent means. Trying this different way, like writing it down here. And 4 for chi-squared. Oh, let's put them right next to each other. Looks better. And 4 for chi-squared is counted data. Does this make sense right here? These are the steps I like to do. This is the way I like to state them out. And we could just put, trying to make this look all pretty. And we can talk about these. Any questions on these conditions? Want me to go into detail? Please. All those please in the chat. And I really like that you can like do all this right here. So I like you can just use a word editor. It's a markdown file. And the independent means. So there's actually a difference between what is called so we're going to go into detail on this real quick. And good question. Oh, let me mark this in the video. Condition talk. Talking about conditions. Okay. And Dee, how's your day going, Dee? I'm sorry I haven't been on Discord as much lately. I've been it's been crazy end of the semester with my classes and teaching classes. Conditions for intervals and tests. Okay. So the independent means. There are times that the means are not independent of each other. And let me show you an example right here to show you not independent means. After that, yeah, of course. You got it, David. Thank you for being here. So here is when the means would not be independent of each other. Okay, check it out. Let's say we work at Kaplan. You ever heard of Kaplan? They do testing, and we have the people come and get a before score and an after score. Does that make sense? They get a before score on a test and an after score. Now, what might we be interested in on these individuals? This is the person 1, person 2. We have 10 people do this. We're probably interested in their what scores. No, it's all right. I think I'm on Reddit too much. So we're probably interested in what? Someone comes in, they take the ACT. We're probably interested in their after, but we're also interested in the what. Like we'd be like, for this person, we'd be like, whoa. And this person would be like, oh man, I wish we had helped them more. We're probably interested in the what's of their scores. We're probably interested in the what's of their score. The difference, exactly. Now that makes this a what test. By analyzing the difference between their scores, that makes this for certain a what test. That makes this a what test? A 2-sample T. And so you could actually just go over here and analyze the difference. And actually, we want to do this one first. This one minus this one. And you could just find, no, wait, we actually do want to do it the other way. I stand corrected. Equals this minus this. There you go. So you could analyze the difference. Now, here's the thing. Isn't it safe to do better? No, I think everyone always says that. That's one of the, DD, I've heard that. I wish I could throw some points, but DD, I've heard people say that, like, oh, IQ tests and standardized tests and SATs. But with the SAT and ACT, it's based on, like, there's prep books and stuff and prep places, and definitely it can help. And I totally think so. But no, SAT and ACT tests like this, prepping helps. Like the GRE, GMAT, and MCAT and PCAT, all these, there's a billion tests, right? So with this in mind right here, think about this. Does someone's after score depend on their before score? Nice job, David, right there. No, oh, that's my problem too, Didi. I got like 99th percentile in math. So do you think someone's after score depends on their before score? Like if someone made like a 18 before, they'd be more likely to score higher after? Do you think someone's after score depends on their before score? Like the score you make. So David, the score you made after going to a prep place, do you think it depended on? It does. Because if someone comes in with a lower score, it's harder to get towards a high score. Now you could drop in score. This person, who knows what happened to them? That's a little bit ridiculous that you go down that far. But it depends on what you do and like how you study. But if you come in making a 32, you're probably going to come out making it in the high, like you're going to increase, right? So does that mean correct? This is a 2-sample T, and this is what is called a paired t-test, not the one we do, the independent t-test. So Megan got it exactly because your after score depends on your before score. So this is a dependent called paired t-test. What you could have is you could have testing facility 1 and testing facility 2, and it could be that these scores came from different testing facilities. Now, here's the thing. If these scores are from testing facilities, this is person 1 at this testing facility, and this is person 10 at this testing facility, you wouldn't actually take the difference. Does that make sense? Because these are different people. This is not the same person where it's paired. Do people understand this first example? You can take the difference here because it's person 1's before and after score. But in testing facility 1 or facility 1, sounds like a level in GoldenEye. Facility 1, facility 2, this would be different people. Like, this is not the same person. Even though this is first person score, you could just take and put 32 down here and 20 up here. Who follows me? Like when they're not paired, because that's the idea of pairing it. Like these two people have to go together. They are paired, but you could literally just shift around any of these values because you're not actually going to take a difference of it. You're going to find the mean of this and the mean of this. Who follows me on that? Does that make sense, Megan? This is just, we have one testing facility, we have another testing facility. Let's compare the averages of the testing facilities. It's not person goes to testing facility 1 and same person goes to testing facility 2, and then whatever they did at testing facility 1 would be dependent on what they did at testing facility 2. Like if they scored well at this testing facility, we'd expect them to score well at that testing facility. You could set it up that way to see like randomize which testing facility they go to and do a paired test to see like the same 10 people go to a testing facility. Who follows me on this? This is a big conversation of what it means for it to be independent means. Because this would just be, the setup for this experiment is 20 people are tested, 10 go to testing facility 1, 10 go to testing facility 2. Whatever the people do at testing facility 2 would not impact testing facility 1, vice versa. It would just be 10 random people. This one is, you have people do a before test at Kaplan and an after test, and it's the same 10 people. So their score before is going to somewhat dictate to some degree their score after, where people who scored well before are more likely to score well after. So it's not completely independent of their score after. This one, whatever people do, like person 4, whatever they did, is completely independent of person 2. So if that person did well, it doesn't matter. That person 1 did well on the other, it doesn't matter. I don't know. And then the conditions on the chi-squared, really good review right there. Let's talk about that. The chi-squared, the conditions are condition 1, random. The condition 2, 10%. And David, I want you to take a look at this output right here. And how would we check? Just tell me how to check. Don't worry about what you're looking for yet. But how would you check condition 3, which is expected cell count greater than 5? Just tell me, and then we'll go point to it. You too, Joshua. Have a great summer. We're going to head off here soon-ish. How would you check? Good luck to everyone on the test. How would you check condition 3? The expected cell count condition greater than 5. How would we check it? So we need to go and find all the expected cell counts. We've already done that here. So the expected cell counts are going to be row total times column total over grand total. So if you look right here, we found all of them with row total times column total over grand total. We went through and did the equation for all of them because you'd have the counts to begin with. And so you could find an expected cell count. And usually checking the smallest is the best thing to do. There's the smallest, and the answer is not 96. Even though the 4 is here, that's not the smallest expected cell count. It's the smallest observed. Actually, whoa, wait a minute. We actually, am I going crazy? Because we did that one. Oh, it's because of an error. That should be 480. Because I was like, why did we do this one? We did it correctly. I was like, made an error, but we didn't. So you would check this one down here to get the smallest expected cell count. And you can see the math, 100 times 120 over 600. You can check the math. 100 times 120 divided by 600. And that's 20, which we put into our table of expected cell counts right there. And now they're all greater than 5. So we pass. The third condition, the third one I use, is expected cell count greater than 5. We pass. And the last condition is counted data. To check counted data, we just make sure they're both categorical, as in the version A and B of the test and the passing and fail are both categorical. And also you can tell because you have a contingency table and mosaic plot. So yeah, when you have a mosaic plot and contingency table, it makes 2 categorical variables. And this was a really good practice problem here, David. We did it in 23 minutes. So check out, it's at 126. I might end the video here soon, do a little walk before an event. But does this make sense, David? This is practice. Are we going to check the, you kind of, yeah, good question, Kenna, right there. You will check the conditions. You'll kind of mention them and know how to do the expected cell count conditions and check your points if you want. Going to end here in a moment, but check, if you haven't, check points. But know the conditions. And we just talked over all the conditions right here. Random, 10%. And then we pull eyes. And then for proportions, success, failure, at least 10 successes, at least 10 failures, NP, NQ greater than or equal to 10, or NP hat, NQ not, or NP hat, NQ hat, NP not, NQ not, depending on if we're doing, which one we're doing. For nearly normal, what are the sample size amounts for each? And that's a really good question. The way we usually do the nearly normal, let me ask you this. What are ways to check the nearly normal? I'm going to put this in the video too. Okay, what are ways? Let's mention the nearly normal. A lot of people wonder about the nearly normal. So I'm going to try to make this test oriented. Checking nearly normal condition. What are ways to check it? What are ways to check the nearly normal? And so Megan's kind of getting into one of them right now. What are ways to check the nearly normal? Any ideas? How do we check it? How do we check the nearly normal? Okay. I'll tell you one out of the way. Oh, and then when doing the expected cell count, we'll be able to do the whole diagram on scratch. We get flagged. No, you'll be fine. Yeah, the biggest thing is if it's a problem, and usually we don't give a ton of questions right there, and Megan's going into the good question, David right there. Usually we don't give solve tons of things. Usually it's solve one thing. And if it's a calculation question, you're fine. And I really go against false positives. So David, good question. Thank you for asking. Thank you for being here. And check out some of our other review videos if you haven't. So Megan says, the first way, my favorite way, is it unimodal and symmetric? Make a histogram. Histograms are the best way to look at shape right here. So if you make a histogram, it's going to be good if it's this. And let's do, here we'll do, I wish I could add one more pen to this. Add a pen. And the pen will be red. Can we actually add, oh, whoa, they actually fixed this? On Word, you used to only be able to add 3 pens, and then someone was probably wait. Okay, so they literally updated this, and I didn't know. Thank you, Microsoft. So now I can put enough pens up here. Good deal. I'll fix that later. That's been multiple semesters. So the first way is to check right there. The second way is going to be the normal probability plot. Goes by many names, the QQ plot for normality, quantile plot, normal quantile plot. And so we might need a little more space right here. I should have done this underneath it. But the good-looking one is going to be one that has the dots follow the line. The bad-looking one is going to be one that bends around the line. The more it bends, the worse it is. And we have the line right here, which is good. If it stays between, that's good. But this one right here is good, and this one is bad. And now we get to the third way, which will be goodness of fit test, which is testing to see if the normal curve is a good fit. And so the goodness of fit test takes your histogram, and the test itself is seeing if it's a good fit, and this one is a good fit, and this one is a bad fit. try fitting it on there, it's going to be a bad fit. And you would get something where it tries to fit it, but it's not a good fit. And this leads to a p-value. This p-value would be high. This p-value would be low. And this is the test of it. So the test of it is actually right there. So that's the goodness of it test. This one passes it, and this one over here fails it. So that's where the test is. Is the normal curve a good fit for it? This one would say no, because the null is, so if you know the null here, the null would be normal, and the alternative would be not normal. Does that make sense, Megan? Usually, I try to explain this sometimes, but I don't know. We don't go into so much detail on nulls and alternatives at this point. And the last way, which Megan is talking about right here, is going to be, how do we check the? Oh, I'll go back to that. Kind of good question. And the last way is going to be the large enough n condition, which is actually lowercase, and this is central limit theorem. So the steps right here are going to be check the shape of your data, then what is required sample size, and then do you have that sample size or more? And okay, so what is the shape of your data? We have either normal data, skewed data, or very skewed data. And so normal, skew, very skewed. And don't worry, we make it pretty obvious what we're talking about. The required sample sizes for each one are 1, 25, and 100. And just check in. So you would just check your sample size right here. So let me do this right here. Let me go to central limit theorem applet and just do an example. Then we'll answer Kenna's question. Thank you, Kenna, for asking. And so when we go over here to the central limit theorem applet, we can begin it. And let me ask you this. Will the central limit theorem work right here? And will this new resulting distribution down here be normal or not normal? What do you think? Normal or not normal? When I run this, we're doing sample size 2. Will the new resulting distribution be normal or not normal? And I can tell you the new standard deviation is going to be like 6. Not normal exactly. We don't have a large enough sample size. There it is. It's 8.82 divided by square root of 2. And so it's not normal. How about now? Will the new distribution down here with the sample size of 2 be normal or not normal? The new distribution of means of sample size 2, will it be normal or not normal? So the new one now, will it be normal? So you check the shape. You say that's normal. This is how you use the steps. You go, it's normal. I need a sample of 1. So what's my sample size? Well, my sample size is 2. And we just do it, and boom, it's normal. So, and then the normal probability plot. And then we don't do a lot of these. It's a good question, Kenna. We don't do a lot of them. So the normal probability plot is if it follows the line. So I can make some in R really quickly. I love making these. They're easy to make. If you, in R, I have a library where I can write QQ. And let's say here, empty cars. And does that look mostly normal? What do you think? Mostly or not at all? I only want you to say mostly or not at all. Mostly or not at all. What do you think? Does that look mostly normal or not at all normal? Mostly or not at all? Would you say mostly normal or not at all? See that line down the center? Does it follow it? Mostly normal or not at all normal? What would you say? Yeah, mostly. Yeah, mostly. I'd go with mostly. I call this the meh portion where it's like, imagine like a 10-year-old's trying to do this and you're like, okay, put the dots on the line, or a 6-year-old. How about the history notes? That one looks a little bit weird, I will admit. Maybe I do the breaks. Comma breaks equals 10. And see, it's got a little bit of right skew. Let's look at a different data set right here. And we're going to pull up people's time on Facebook. Okay, does that look mostly normal or not at all? Mostly normal or not at all? Remember, the line down the center is what is normal. The line down the center is what is normal. So this is what we should see if it's normal. That's what we should see. Do you see the big difference? I'm pointing out like what you see in practice. So the line down the center is what is normal. And here's our data. Our data is the dots. Our data is the dots. Is our data following the normal mostly or not at all? Is our data following the normal mostly or not at all? What do you say? Is our data following it mostly or not at all? What would you say? This is how often people are on Facebook. Say, yeah, my data not at all. This is very not normal. This is, and then if you look at the histograms, this is the way the histogram looks. That's his histogram. It's extremely right skew. So yeah, we were right to say not at all normal. How about this? So how normal does this data look? Mostly or not at all? Does this data look mostly normal or not at all? There's the previous one. So only say mostly normal or not at all. Let's test. Yeah. You know what I actually did? Random normal generates random data. Random normal data. That this is normal data. It was generated to be normal. So if you're like, this is, all of these are here. As I click and you watch these appear, all of these actually come from normal. Do you see how we give it a little bit of like, it's going to be weird in some spots, but these are actually real ones. You won't know our studio. No. You don't need to know our studio at all. I just do it to make graphics really easily because I can show you tons of QQ or normal quantile plots, normal probability plots. I can make them like this using R. So you're not required to know it or use it. You do see it like an Excel makes it, but it's easier for me to just instantaneously make like a million of these. And what's really cool is, watch this. I could probably do it. Well, I'm going to cheat and use ChatGPT. But make a 3x3 grid of different normal quantile plots in R that look awesome. Okay. So coding, I think, is like ChatGPT. There's a lot of cons to it, but coding is so much easier. Patchwork puts things together. Which I have to watch because sometimes I'll forget how to code things because I'll GPT stuff. But Tidyverse loading up. Oh, don't I have patchwork? I don't have patchwork on this computer. I installed all packages. See, it didn't expect me not to have it. There we go. That installs the package for you, and now we can run it. And here is our grid. Wow, look at this. So it's showing you different ones, and these are different normal probability plots. But the normal is the one that it didn't put the meh bands in it. But do you notice the more normal it is, wide normal? I don't see a difference between that one. Outlier mixture, it's got a bunch of high outliers. Bimodal, it's got a low mode and a high mode. You're not meant to know it to this extreme, because even I could barely tell you. Long tails on the side, like goes above there and below there expected. Because the line's the expected normal. Left skew. I know left skew, right skew really well. Yeah, Claude Code. I'm going to try to get more into Claude Code over the summer. But I mean, it's so cool, like how you can just like get things like that. And I should probably know all of these graphics really well, but I mean, it made a really good, that's about as good as it gets on showing you the difference. The only thing you need to know in 201, so Kenna, here's the big thing to know. The biggest thing to know in 201 is this first one. The more normal the normal probability plot is, the more it follows the line. Also, conceptually, knowing that a normal probability plot is a way to check normality. Does that make sense? What would you not, here's my last question right here. What would you not check normality with? So this is the key concepts right here. What would you not check normality with? There's a lot of answers to this. What would you not check normality with? What would you not check normality with? There's like infinite answers. Don't check it with your hand sanitizer. Don't check it with your duck. But bar chart, exactly. Megan's got it right there. Bar charts, because bar charts are for categorical variables. Up there, you can see bar charts. So bar charts would not check normality. Pie charts would not check normality. You wouldn't really use a box plot. It's just not good at showing the shape of the data. Box plots can hide features. Box plot's not and David, that's a good answer. It's like here, I'll show you, like, watch this. Let me go back into R. It's just a really easy way to make graphics. So I can make a box plot really easily if I just go to think box plot, right? Yeah, box. No, wait. Box plot? There we go, box plot. And then is this data, is that data normal or not normal? Do you see, does that make sense? It's really hard to tell. You can't really tell. That's, box plots don't really show shape really well. Histograms are going to give you a better idea. I've got capitalization on. Histograms are going to give you a better, no, I can't spell. Histograms are going to give you a better idea of shape, and you can see a little bit of the right skew. You can kind of see it in the box plot, but the histograms give the better view of shape. And then we have other ways of doing it, and the central limit theorem is a really good way too. The central limit theorem. We've made a lot of good notes today. If you look, probably my favorite note sheet was this one that we did right here on confidence intervals. So really good note sheet going over these ideas. Well, I think we will stream again tomorrow. So with that, any last questions right here? Anyone say goodbye? I'm doing a lot of online streaming. It's time to head out. A lot of emails. You're welcome, Megan. Good work. With that, we're going to leave now. Bye for now, everyone. Bye. Oh, I'm in the car. I think almost about the same time. I'll see how it goes. I'll send an email, David. And great work. I don't know why I clicked the car. Here, wait. Ah! Woo! I'm still here.